Hi. So in this session, we're going to be talking about ML frameworks for generative AI development. And if you're wondering who I am, that's who I am. I'm Robert Crowe. I'm a product manager at Google in the frameworks team, focusing on JAX, open source, and Gen AI. We're going to be talking a lot about both. So to start with, I think everybody here is really familiar with the last couple of years, what we've seen in some of the compute demands that have grown from the early days of the transformer in 2017 up until maybe Palm 2, which over 1 billion petaflops of compute required to train seemed like a huge amount. And today, models like GPT-4 or Gemini are way beyond that. GPT-4 is estimated at something like 1.8 trillion parameters, which requires about 21 billion petaflops. Try to wrap your head around that to train. A data set with 13 trillion tokens, 13 trillion, and something like $63 million for each training run. Now, these are estimates. And people who should know, like Mustafa Suleyman, who's one of the co-founders of DeepMind, expect that this is going to continue to grow at a fast rate. He says he expects it to be 10x within 12 months. And within 2 or 3 years, something like 100x. So efficiency, compute efficiency, is incredibly important. Not like it wasn't important before, but now it's really important if you're working in Gen AI. And of course, Gemini is one of those models that is huge, and we've had amazing results with it, and you've seen some of that, and we've talked about it today in other sessions. So one of the things that we're seeing is that, so JAX is a framework for, that's used in Gemini, and it's used in a lot of things around DeepMind. So actually throughout Google, we use JAX for pretty much all of our Gen AI work, and a lot of our other work as well. So most of our research is done in Gen AI. So you probably remember AlphaFold from a few years ago. It achieved amazing results. It discovered the protein structure of the approximately 20,000 proteins which make up a human. And it went on to find the protein structures of all 200 million known to man. Huge advance based in JAX. Palm 2, we remember Palm 2, it was a huge advance in Gen AI. And now we have Gemini, which we've talked a lot about. And BARD, which seems like forever ago. It was just under a year ago. So I mentioned JAX a couple times. What is JAX? Well, in a nutshell, JAX is autograd, so automatic gradients, and XLA. So that includes differentiation, vectorization, and a just-in-time compile that's really focused on GPUs and TPUs becomes incredibly important. We'll talk a lot about that. And composability is a big aspect of JAX as well. This is kind of a typical JAX stack. It's not the only one by any means. JAX is a really flexible structure and framework. It's designed to be modular and adaptable. But this is kind of maybe the canonical stack. So Flax is a neural network library that layers on top of JAX. Orbax is a set of utilities like checkpointing and exporting. And Optax is where all the optimization and gradients live. We'll talk a little bit more about each of these. Those sit on top of JAX, which in turn sits on top of XLA. And we'll talk about XLA in a second. Right now. So XLA is a compiler-based linear algebra engine. So it's really focused on linear algebra, which of course is the core of ML and AI. It targets CPUs, but really GPUs and TPUs and other accelerators as well. So what XLA is really looking to do is to try to get the best performance without, before you're doing a lot of tweaking out of your code. It's a compiler, it's a runtime, and accelerator-specific optimizer. And it's fair to say it actually delivers supercomputer level performance. XLA is the core compiler of the OpenXLA project, which is a suite of ML infrastructure tools and a consortium of AI industry leaders, including NVIDIA, PyTorch, Hugging Face, Anyscale, Intel, and a long list of others. We're actually having a dev lab later this month with something like 17 partners coming. And you can join as well. OpenXLA has an active community, and you can join the community meetings. If you go to GitHub, they're linked from there, or you can go to openxla.org. All right, who's familiar with NumPy? Sure. Oh, yes, that's what I want to see. Okay, good. This is NumPy, so we're all familiar with it. Okay, I get to use a laser pointer. Any cats in the room? No? So, you notice the calls here to NumPy, right, after the export. Really familiar code. This is a predict and a loss function. How would we do that in JAX? Well, just like this. Instead of NP, we have JNP because we're importing from jax.numpy. And the rest is all the same. So that gives you really familiarity, but when you do that, you get all that acceleration from XLA. And if you gave it sharded input, it's going to distribute that across multiple accelerators. We'll talk about that some more in a second. There's transformations in JAX, and they're composable. And we'll show some composition here in a second. These are 3 out of a whole bunch. But these are maybe the most important ones. I hate to say that, but anyway, JIT certainly is incredibly important. JIT is your just-in-time compiler that gets your code compiled to really low level for your accelerator and sets it up for distribution and so forth. VMAP is for doing vectorization, which if you've worked in linear algebra, you know how important that is. And grad for gradients, because of course, gradients are everything in ML. So here we have those same predict and loss functions, but look at the bottom here, where we're using JIT and grad and VMAP, and we're composing them in a functional style. And that allows us to do things like take the gradient of our loss function and just-in-time compile it. We'll talk in a second about the performance that we get from that. And then the other one is the same kind of a thing. We're doing some vectorization. So when we use JIT to speed things up, and this is all we're doing to speed things up, we're creating a CELU activation function. We're giving it some data, and we're timing it. This is without using JIT. And what we see is that a loop takes about 2 milliseconds. Okay? When we do use JIT, we take that same CELU function, we apply JIT, and there's different ways to do it. We could have used a decorator for this. We do some warm-up to go through the just-in-time compile, and then it's 150 microseconds per pass through the loop. So incredible speed up. And all we did was JIT. Oh, sorry, wrong button. So when you give JIT sharded data, it's going to automatically do parallelization. And we'll look at some options too. You definitely have a lot of options here. So that means that it could either be directly, like we just saw, or it could be in a decorator. It's going to, if you give it sharded arrays, it's not going to copy those to a single device. And it is going to do the communication primitives that you need for things like all reduce. All right. So how does JAX help us with Gen AI? Well, there's some challenges that we all know, and if we didn't know before, we do now. Very large compute resource needs. Models are huge, billions of parameters, only getting bigger. Data sets are huge, trillions of tokens. And everything's changing fast. There's new stuff all the time. So adaptability is incredibly important here. And at the end of the day, what we're trying to do is manage our costs. So there's the cost of training and serving our models, also the cost of developing and adapting our models. So here's an example on a small model. So even with a small model, you can see JAX is not only faster, it's less expensive. If we scale that up a little bit to a 1.8 billion parameter model, it only increases. The difference only increases. So we start to see even greater cost savings, even greater speed up. And how far can we take this? 50,944 TPUs in one training job. And pay attention to the graph on the right. The dark dots there are the ideal line. If it scaled perfectly, theoretically, that's where we would be. And you can see the light blue dots, which is what we actually achieve, are only slightly below that as we get up to very high levels of chips, something like 8,000 chips. So efficient scaling and easy scaling as well, because we can get a long way only doing some basic stuff in the code before we start, diving into kernels and so forth to really squeeze the last few bits out of it, which we'll talk about. Because you can do your kernel code gen. There's two different ways to do it. We'll talk about them. And you can control your cross-device communication with shard map, also known as SHMAP. So here are the two ways to create kernels with JAX: Triton call and Palace call. Let's talk first about Triton. So Triton call is used to create, you can create your kernels with the Triton EDSL. Triton call is used to call them. And you pass it JAX arrays and so forth. Fairly standard, really, if you're familiar with Triton. And this is a fairly standard Triton kernel. It's a small one. So that gives you an idea of, what it looks like, and then how you call it. So you see I've got a kernel called add kernel. I'm going to call it with Triton call and pass kernel equals add kernel. Fairly straightforward. Palace. So you can also use Palace. And the nice thing about Palace is you don't leave JAX. You stay in the JAX syntax and idioms and code and semantics and so forth. It's also transformable. And it's easier debugging with the CPU interpreter. So let's look at some Palace code. Here's, again, our Triton kernel. That's the same kernel in Palace. Which code would you rather write? So, easy and efficient scaling. It includes parallelism and sharding. So to do parallelism, one of the key things to use is jax.deviceput and give it sharded data. JIT works along with that to do parallelization, and then you have a number of different options for the types of parallelization you want to do. Data or tensor or pipeline parallelization. So shard map or SHMAP is used for multi-device SPMD parallelization. You can express axes, the different multiple axes of the parallelism in one go. You have per device shapes. You can explicitly define your communication collectives. It's eager. So one of the nice things is when you're working with this, you can step through it in like a REPL and do debugging and so forth. But of course it composes, just like everything else in JAX. AQT, accurate quantized training, is another way to speed up your code, so quantizing your code. And this is quantization-aware training, so you're quantizing at training time. It's designed for JAX. We're going to take a look in a minute at an example of quantizing from FP16 to int8. This is that code. So let me walk you through this a little bit. We've got a class that we're defining that's a very simple model. And we've got a call with two dense layers and an ReLU activation function. This is kind of the key part of that. So it's going to pick up this config that we're going to give it when we call that. So now we're going to set up a config that is setting up for 8-bit integer quantization. If we don't give it anything, we just pass none, this is going to be FP16. So that's going to be our floating point 16 version of this. But if we just pass it this config that we just created, now it's integer 8. And that's all we did. That's quantizing our model. So let's talk about some different kinds of scaling, some different kinds of distribution. We can do data parallelism, very simple data parallelism, where we're going to take the model, the entire model, and put it on each of our accelerators. And then we're going to shard our data and give each of our accelerators a data shard. So we're splitting up our data amongst our accelerators, our GPUs or our TPUs. That's fine, great, works fine. If you have enough memory to fit your model, fine way to go. If you don't have enough memory to fit your model, you want to shard your model. So in that case, you shard your model and you shard your data, and then you bring everything together. So what does the code look like for this? Well, for data distribution, it's pretty simple. We've got, we're going to shard our data here, but our model stays as one model. So in that case, we're duplicating the model across our accelerators, we're sharding our data. If we look at fully sharded data parallelism, FSDP, is very similar as far as the code. There's a slight change here. Now we're passing it this batch from our mesh in our partition spec, and now we've moved from data distribution to FSDP. Portability. So in a lot of cases, you're going to want to take your model and you're going to want to work with it, maybe deploy it, maybe you have different teams working in different environments, so you need to be able to move between environments. Accelerator portability is really important then. And when you have a code base that you want to share amongst a number of teams, you don't want to have different versions of that code base for different hardware or different accelerators. So it becomes important, portability and making sure that you don't get failures like out of memory and so forth between different sets of infrastructure and different accelerators. Cohere did an interesting study earlier, late last year, looking at exactly this, because they saw the importance of this. So in their study, how did we do? Well, JAX, both in terms of success for GPUs and for TPUs, was the highest they found. It was the highest rated framework that they tested. Flexibility. We talked a second ago about the importance of adaptability because things are changing fast. So you need to be able to adapt your code and move quickly, and you don't want to spend a ton on development costs when you do that. So what do developers tell us? Well, here's an example of what Stone DAO called sense of tranquility. when moving his code into JAX. Because it not only became faster, it became better. Similarly, Liu Gao decided to move to JAX because it takes many of the demanding tasks away from him. He doesn't have to worry about it, such as managing communication of activations and gradients. Jiazheng Chu used to write CUDA kernels. That's probably some of you have written CUDA kernels. He's working with GNNs, and he moved his operations into JAX and discovered that the performance was much better than he was seeing in another framework. Similarly, Ross Whiteman saw that JIT-JAX, in his words, ran circles around his familiar code in another framework. So, coming back to the stack, Flax is the neural network library that layers on top of JAX. It's for neural network work anyway. There's lots of other kinds. This is probably the most used library. There's others out there though, like Haiku. Orbax is a set of utilities that includes things like checkpointing and exporting, and Optax is gradient processing and optimizers. So Flax gives you end-to-end flexibility for neural networks. There's actually two neural network APIs in Flax, one called Linen, get it, Flax, Linen, and the other one NNX. I don't know where they got that. It's designed to be kind of minimalistic. It's designed to be functional. It's a functional style of programming. And this is what the code looks like. So very similar to some other frameworks that you might be familiar with in terms of structure. This is, creating a multi-layer perceptron with 2 dense layers and a ReLU. Very similar, very familiar code. You're not having to do anything weird here. But there's also Keras 3, which layers on top of JAX and does not really require those other libraries because it's more of a batteries included framework. And probably a lot of you are familiar with Keras because it's been around for a while. It's used by CERN, NASA, National Institutes of Health. There's different styles of programming that you can do using Keras, both functional and sequential APIs. This is what it looks like to use Keras 3 with JAX. So Keras 3 gives you the ability to deploy into JAX or into PyTorch or into TensorFlow. So you can see really the only change here is at the very top where you're setting up your OS environment variable to tell it which backend to use. Orbax we talked about a little bit. Again, checkpointing and exporting. Optax is gradient processing and optimization. That's where your optimizers come out of. And there's an open source community with a whole bunch of other stuff. So Levanter, coming out of Stanford, EasyLM, coming out of Berkeley, AXLearn, coming out of Apple, and a bunch of others, Objax, which actually came out of Google, JRAF, out of DeepMind, Equinox. Especially if you're doing scientific computing, Equinox is a great library to use. A lot of people like that. Checks we should almost include in the canonical stack there because that's where your test utilities come out of, or at least that's a great library for that. And RLAX if you're doing reinforcement learning. And there's a ton of others. I would recommend you go to that link there. There's a long list of libraries that have been built on top of JAX. But you don't have to actually start from scratch. We give you things like MaxText. So MaxText is a full model implementation that's been highly optimized, and it's really incredibly fast and clean and elegant. You take MaxText, and the idea is you fork it. So you're going to take it, create a fork, and then make that whatever you need it to be. But it gives you a great place to start from, because a lot of the structuring and efficiency has been done for you already. It also includes implementations for a bunch of other models, including GPT-3, Llama 2, Mistral, and Gemma. It's high performance. It scales really well. You remember that 50,000 TPU thing that we looked at? That was done using max text. Easily forkable, batteries included, written in pure Python. So even though it's very efficient, still in pure Python. So how efficient? Well, it typically achieves something like 55 to 60% model flop utilization, which if you're familiar with MFU as a metric, that's really high. MFU, if you're not familiar with it, is the ratio of observed throughput, tokens per second, relative to theoretical maximum throughput of a system operating at peak flops. There's also max diffusion, which we announced today. Or actually, no, I'm sorry, we announced that back in February, or we released it back in February. I think we announced it today, something like that. Anyway, max text is for LLMs, max diffusion is for diffusion models. So very similar, it's the same kind of approach. It includes the Hugging Face JAX models, and includes stable diffusion as well. So stable diffusion 2, 2.1, and XL. XL is inference only. Serving. Well, at some point, you want to serve your model. So we have Jetstream. Jetstream we just announced, and Jetstream is kind of early. It is a throughput and memory optimized engine for LLMs, and has a lot of great inference optimizations, things like continuous batching, weights quantization, KV cache quantization, ragged attention, and prefix bucketization. So it's designed, really it's based on the engine that we use internally. So for our needs, this thing has been, really built out to be as efficient as possible. This is what it looks like to start up and test a server. So really easy to get one of these things going. It is single host at the moment. Stay tuned. Gemma. Well, you guys have heard a lot about Gemma and recurrent Gemma and code Gemma now. You're familiar with the fact that Gemma is an open model. It's an open weights model. So you can take Gemma and run it wherever you would like. It's available on Hugging Face. It's available in Kaggle. So one of the things you can do is run Gemma in a Kaggle notebook for free. And here's how you use it with JAX. So this is pretty basic. We're going to set up, first of all, our tokenizer. And then we're going to create our transformer and just set it up. And then we're going to create a sampler so we can do inference. And then we're going to call it with a prompt. In this case, what is the meaning of life? Anyone know the answer? 42, that's correct. Very good. If you do it in Keras, it's even fewer lines of code. That's it, 3 lines. Same answer though, still 42. So we mentioned Keras a couple of times. Let's dive into that a little deeper. Keras is multi-backend. Actually, kind of goes back to the very early days of Keras, but it's a full rewrite of Keras. It's gone from 135,000 lines of code to only 45,000 lines of code, and yet we added all this stuff. It now supports deploying into a TensorFlow stack, or JAX, or PyTorch, or even NumPy. The NumPy backend is inference only. It's a drop-in replacement for what many of you are probably familiar with in TensorFlow Keras, which was Keras 2. This is Keras 3. All you're going to do is change your imports. And since it includes JAX, it includes XLA compilation, so you get all those performance benefits. Go to Keras.io and check out the performance study that they did and the speed up they get when they move to JAX. So one of the things you can do is use Keras.ops to create functions that can be used in different environments. It does include, one of the things that includes is NumPy, the NumPy API, which is pretty much a full implementation of NumPy. There are some slight differences like in-place updates. You can also use the models and layers that are going to work the same in TensorFlow, JAX, and PyTorch. And you can even flip it around the other way. We'll take a look at this in a second. So this is using Keras ops right here. So we're creating a class here. We're creating a module, token and position embedding. We're going to use Keras ops. And what that will allow us to do is once we've created this module, we can use it in a TensorFlow model or a JAX model or a PyTorch model. So we can create modules like this in Keras and use them across different frameworks. If you're creating a code base of libraries, this becomes pretty nice. You can also go the other direction. So in this case, here's the same module, but we're going to use Torch to do our calls. And then we can use that in a Keras model. So we can actually go both directions. And you can see the same thing here with TensorFlow, using TensorFlow to make our calls, or JAX to make our calls. And we can use those in Keras models. So, JAX and Gen AI. Why is this a marriage made in heaven? Well, we know that compute demands are just crazy. We're looking at models today that are incredibly expensive to train with huge data sets. They are huge models in terms of the number of parameters. The challenges are there. We know it's only going to get worse. People who should know these things expect huge growth in the size of these models. And the reason for that is because we've seen that as models grow, they're able to do a whole class of different things that we, just 5 years ago, we would have thought were 50 years away. So we have all those challenges. How do we meet them? At Google, we meet them with JAX and the XLA compiler, which is the central part of OpenXLA, a community project with a whole bunch of partners that we talked about earlier. And you can take JAX and apply a lot of optimizations with Triton and with PAX. You can do sharding. JIT as a just-in-time compiler becomes very important. You can do quantization. And we saw, with just a couple lines of code, quantizing a model from FP16 down to int8. It's a modular, layered design that is designed to be adaptable and flexible because as things move forward, that becomes really important. And there's a wide selection of really high-level APIs that you can use with it. Two of them, Keras 3 and Flex, we've talked about. But there's a whole selection of others if there's other things that you want to use. Objects, Equinox, Arlex, JREF, lots of them. People have really taken this and molded it to be what they need it to be. And if you want to start from a nice code base of a model for an LLM or a diffusion model, you can take Max Text or Max Diffusion, fork it, and you're off and running. And of course, there's Gemma. And it's the Gemma family, really. It's Gemma itself, but recurrent Gemma, code Gemma, and possibly there's some more on the way. Here's some resources for you. I'll leave that there for a second if you want to take a picture. Here's a QR code if you want to tap into some special offers. Give that a second. And of course, your feedback would be greatly appreciated. And that's my talk.